forgot to start the recording.
I just noticed this entire time that you were talking, you weren't recording.
So should I go backwards? Yeah, I better.
Probably, because if somebody goes back on and rewatches this, which I don't know if anybody actually goes back in and rewatches them, really. But if somebody actually does watch it, I mean,
yeah. Okay.
better go over it.
Let's see if I can remember what I said earlier. I was talking about putting a salt in solution. What's the I shouldn't say what's the pH because that implies quantitative. But is it acid, basic, or neutral? Those were qualitative assessment. Okay, so what happens when a salt goes into solution? Well, you can think of a salt in terms of its derivative, or how it was derived. So if you have an acid and a base, then you get the combination of that cation and that anion gives you the salt. So you can think of it in terms of what was the origin of the salt? Where did it come from? Whether it did or not, it'll answer the question for you. If I give you a salt and say, put it in solution, do you get an acidic, a basic, or a neutral solution? Okay. So let's go look at some possible salts. Sodium chloride. How about sodium fluoride? Ammonium. Chloride. That's good. And magnesium acetate. Okay, so we put them in solution and we just say, all right, what's their concentration? Well, we say, I don't know, 1 molar, 10th molar, as long as they're the same. Then we don't throw that variable into the mix. Okay, so what was this derived from? If it was formed as a consequence of an acid-base reaction, sodium hydroxide, hydrochloric acid, both strong base, strong acid, neutral solution. Right? And if you titrated one against the other, you would get the equivalence point at pH 7. How about this one? Well, that's a strong base, but what's HF, hydrofluoric acid? It's a weak acid. So that means the solution would be basic. Rule of thumb: strong base, weak acid, basic solution. Now, we described why that happens in solution, and it's basic not because of the sodium, but because of the fluoride. Right? And maybe I'll just refresh your memory. Sodium goes in solution, it reacts with nothing. It does not react with water. Why? Because if it comes from a strong base, it's a very weak acid. It has a very, very weak attraction to protons. Or hydroxyls, excuse me, hydroxyls. So it doesn't produce this reaction. Would be your proposal, right? In case of sodium ions, that doesn't happen, right? Because if sodium hydroxide is a strong base, it completely dissociates in water. Sodium has no attraction for the hydroxyls once you get it in water. Right? So that reaction doesn't happen. What does happen when you put this in solution is the fluoride ion. HF, hydrofluoric acid, is a weak acid. So it does not want to give up hydrogens. HF does not give up hydrogens easily, which means if it's a weak acid, then its conjugate base, fluoride, is a strong base, which means it has a strong attraction for hydrogens. So what it does is when you put that in solution, it reacts with water, produces HF and hydroxyls, right? Hydrogen, hydroxyl makes water. So this is left over from that reaction. That's why it's basic. But back to our rule of thumb. If the salt is formed from a strong base and a weak acid, you get a basic solution. How about this one? That's formed from a strong acid. Ammonium is a weak base. So it's an acidic solution. Now, why is ammonium a weak base? It has very weak attraction. Well, let's say if it's a weak base, that means it had to be derived from a strong acid. Well, actually, ammonium, let's put it this way. Back up. Ammonium, what is it going to do? Ammonium is going to react with water to transfer a proton to water. That's the acidic side of the reaction. Just like this was the basic side, the acidic side means that this one wants to give up its proton very readily because it prefers the ammonia form. And if you recall in the complex ion lab, I added an appendix at the end and proved to you that when you put ammonia in solution, you could potentially have this reaction. Oops, sorry. It's already used up. That's it. You could potentially have that reaction, but the equilibrium constant for that reaction says it's going to be over here. 99% is going to be this one. So that means that it wants to be over here, preferred here. So when you put that in solution, it reacts with water and makes the hydronium ion. All right, so now we've got neutral, basic, acidic. How about this one? What do we have here? Well, acetic acid is a weak acid, right? But what is magnesium derived from? Magnesium hydroxide, right? Remember that all alkaline metal hydroxides and all alkaline earth hydroxides are strong bases. The difference being that the alkaline metals are completely soluble, whereas the alkaline earths are much less soluble. In fact, some charts would identify them as insoluble. But we know from our study of equilibrium that the insoluble and soluble are relative terms. And while you may say something is insoluble, there will always be some of it going to solution. It might be a small amount. So that small amount that goes into solution for magnesium hydroxide is a strong base, which means when it goes into solution, it completely dissociates. which is the definition of a strong acid or a strong base. Complete dissociation. So when this salt goes into solution, weak acid, strong base, you get a basic solution. All right. So now, I see Isaac's name. Let me mark him down here. So we got Kessa and Isaac. All right. And what I'm doing, Isaac, is I'm just sort of hopscotching topics that are good candidates for the final exam. And I'll continue with this on let's see, what's the day? Thursday, on Tuesday, so that we can get all of our topics covered and hopefully give you enough time to prepare for the final exam, which is due on Thursday. Okay, so covered that one. Dissolution of a salt. What pH, not what pH, is it going to be acidic or basic or neutral? Now we're going to extend that topic to the discussion of conjugate acid-base pairs. Okay, conjugate acid-base pairs. What constitutes an acid-base pair, a conjugate acid-base pair? You have to look at the definition, actually. So if we say we're going to react an acid with a base, and in this case, I'm just going to take the acid and put it in water. And the acid's going to react with water. And what's it going to do? Well, the water's going to pick up a proton, and the acid's going to lose a proton. Okay? Now I chose an acid with two dissociable protons for a reason. Because there are two defining principles for an acid-base pair. One is that A has to be the same A on both sides. For instance, if this were a sulfate, then you'd have that sulfate over here. Of course, in combination with a proton, that neutralizes one negative charge. That's why overall is -1. Over here, these two protons balance those two minuses. That's why that whole group is neutral. So the A has to be the same on both sides. The other condition is that you can only lose one proton in the process. From here to here represents one proton movement. Now, why do we even bother with that? Why can't we just say, all right, we know, especially if that's a strong acid, both of those protons are going to be gone? Well, yes and no. The first proton, yes, for a strong acid. The first proton is completely gone. It's all the way over here. But you'll recall that the second proton is less likely to dissociate because you're trying to get a positive charge to leave a negative charge. It's more difficult to do that. That's one way of looking at it. So in a conjugate acid-base pair for this one, we would have the acid and its conjugate base like that. There you have the A's match, and you only have one proton lost. That's true. Okay, now let's use real world. Suppose you were given this conjugate acid-base pair, maybe, and asked to say, is this true or false? All right, let's say we have, let's use diprotic there and there. Okay? Is that true or false? Conjugate acid-base pair. It's false. It met one condition, but not both. Those two groups are the same on both sides. That's true. But this, you've lost 2 protons. And that, by definition, is not the conjugate base of that acid. What would be the conjugate acid of that thing? The hydrogen sulfate ion would be the conjugate base of that acid. Okay, that would be true. Now, suppose the American Chemical Society test from which I derived your final, the developers of the test were sneaky. And they said, okay, we're going to say, leave it like that. 1 proton's lost. But we're going to do this. Now, where's your dilemma? The problem is, if you focus on this one and you don't check that one, then you get it wrong. Right? Because the A's are not the same in this one. That's not the same as that. 1 proton, yes, but not the same counter ion, anion. Right, so that was false. Just a word of warning. Okay. Now, let's see. Let's extend our definition of acid base. Right, Bronsted-Lowry. Lowry. Definition just says an acid is a proton donor. Right? So that means a base is a proton acceptor. And they always go in pairs. You can't have one without the other in a reaction. When an acid loses a proton, it's got to go somewhere. Protons do not float free in solution, even though we write them that way sometimes. For instance, in the oh, got another visitor. Let's see, Heather. Okay. So I'm just reviewing possible problems that could show up on the final. And I started off with acids bases. So we've covered a little bit of it already, and now I'm going to extend the definition from Bronsted-Lowry to Lewis. But I was just mentioning the fact that acids and bases, when you have a proton donor, you always have a proton acceptor. Protons do not float free in solution, even though we write them that way sometimes. Okay, so if we take this definition and try to extend it to use as a Lewis acid base, then if we begin by limiting our discussion to proton transfers, then if we look at something like, let's take a real world. Let's say we have this acid, and in solution, well, let's be kosher. We're going to put it in solution. What's going to happen? We know that that proton goes to that water and leaves us with the conjugate base. Okay. So that satisfies our definition for the Bronsted-Lowry. But how do we transpose that into Lewis definition? Well, Bronsted-Lowry were focused on protons only. Lewis wanted to make acid-base reactions possible in non-aqueous solutions. So in that case, you can't focus on protons exclusively. I mean, it still happens, but it doesn't happen with water. Pardon me. Instead, Lewis focused on electron pairs. So, if we've got a bond here of some sort between hydrogen and chloride, and then that bond represents 2 electrons, right? 2 electrons. So you could view it as 2 electrons over here, 2 electrons over there. We really don't know where they are. They're just moving back and forth in that bond. Then what has happened in the process of going from here to, say, there? Those 2 electrons are now residing with the chloride ion. So that means that the if this is the conjugate base, then the acid has transferred electrons, and let's see, proton donor then would be here. In the Lewis sense, it's an electron pair acceptor. Okay? So if this is the acid and this is the base, then the electron pair acceptor is here. This is accepted electron pair in order to produce that product. And the base has accepted the proton from here, which makes it here. But in the process, an electron pair has been donated. And in the process, we end up with unequal charges. In other words, the electron pair acceptor has taken the electron pair to produce that base, and the electron pair donor has taken this proton off its hands to produce that. So if you just need to memorize the definitions, the relative to Bronsted-Lowry, if it's a proton donor, it's an electron pair acceptor. And if it's a proton acceptor, it's electron pair donor. Okay. Let's see. We didn't go into a whole lot of detail with Lewis acids and bases because that really would be stepping on organic chemistry's toes. When you get to organic chemistry, if that's where you're headed, then pause for a moment. That's one of the hazards of working from home. Okay, let's see, where was I? Right, Lewis acids and base are really important in organic reactions, because many organic reactions have to be conducted in non-aqueous solutions because water can be a reactant. And sometimes the reaction of water with your reactants is not a desirable reaction. It's considered a side reaction. Okay, so let's talk about buffers now. You have to get down. Let's talk about buffers. What constitutes a buffer? A buffer is any solution in which the pH is relatively stable. It's not constant, but it doesn't move much when an acid or a base is added. Okay. We can't say the pH is constant. pH is relatively stable for a buffer. And that's only if it's in the buffer zone. Okay. So let's look at some examples and see if you can pick out the one that is a potential buffer. So what's required for a buffer? Let's look at Henderson-Hasselbalch, because that's central to the formation of a buffer. So if we want to know the pH, we need to know the pKa of the acid, the weak acid, and the log of the concentration of the conjugate base with the acid. Okay, so that's the generic form of Henderson-Hasselbalch. And this corresponds to a titration of, we could do acid or base, but let's just make it an acid. So we start off here with pH, and then we have added base. So we start off here, as we add base, the acid is going to slightly become more acidic, and then it's going to level off. Not exactly horizontal, but relatively level, up to a certain point, and then it skyrockets and flattens out. So at this point, you have equivalence. That means the number of protons and the number of hydroxyls are equal. I'll say it that way because some acids are diprotic and some bases are dihydroxyl or more. And the only way to say it properly would be to say the number of equivalents of acid equals the number of equivalents of base. But this is your equivalence point. At that point, if you add all the base, then you've neutralized all of this. You've taken away that completely. So that would be 0, and your expression would be infinity, which would be meaningless, really. So the point at which the buffer occurs is over here, right? And when you can see it in the titration curve. And that's exactly 1/2 of the equivalence point, right? And 1/2 of the equivalence point is where? It's where that one equals that one. When this expression here is equal to 1. So what does that also tell us about the buffer zone? It also tells us that this expression, if that's 1 for that place, then this whole expression is 0, because this is common log. So 10 to what power equals 1? 10 to the 0 power is 1. So this expression is 0, and in that case, the pH at this point is equal to the pKa. So if you know the pKa of your weak acid, that is smack dab middle of the buffer zone. Okay. So back to detecting. Whether you have, let's see, I don't want to erase all of that. Might want to talk about it a little more. There we go. For example, say we have Say we're going to mix two solutions together. Okay. Will that form a buffer? Well, we go back to the concept of conjugate acid base also. The A's have to be equal. They have to be the same. They're not the same. This cannot be a buffer. There's no way to form a buffer from that. Another example. How about this one? Okay. Can this one form a buffer? Well, look at the acid, right? That's a strong acid. Can't form a buffer with a strong acid. It has to be a weak acid. And we talked about that in class, I think, because the addition of protons or hydroxyls to a buffered solution, the reaction depends upon having a weak acid available. So that one can't form a buffer either. Strong acid, strong base, out. How about this one? It's almost the same scenario. If you put these together, this one is going to be neutral. This one's going to be acidic, and it's a strong acid. So the solution is going to be acidic, but not buffered. Even though you have the A's are equal, you don't have the ability to capture protons with a weak acid. How about this one? Can we form a buffer from that? Yes, we can. Only in this case, which side is the weak acid? That one right there. No. That's a strong acid. This is actually the converse, forming a buffer from a weak acid and its conjugate base. We form this one from a weak base and its conjugate acid, which is valid. But in order to use Henderson-Hasselbalch, you may be given a pKb that's associated with this one. In order to use Henderson-Hasselbalch, you'll have to derive the pKa in order to use that. And then you've got to decide what's your conjugate base and your acid. Okay, that's where this one could get sticky in terms of calculations. But this one, yes, that could form a buffered solution. Another possibility is this one and this one. That's a good example. That's an acetate buffer. You have the weak acid and its conjugate base here, and sodium is a spectator. So if you put these together, if you had, say, 0.5 molar here and 0.5 molar there, and you put equal volumes, so equal volumes means equal amounts of that as opposed to that, then you would end up with a perfect buffer solution for acetate. Okay. While we're stream of consciousness, I mentioned pKa, pKb. If you know the pKa or the pKb, how do you find the other one? Well, I just put it up here. Let's see. pKw is equal to pKa plus pKb. Right? We derived that formula in class. But if you know I see, is that going to help me? Yeah, it should. Hold on a second. Am I doing that right? This would be 14 for water. So if this acid were, say, I don't know, acetic acid, 4.7, then pKb would be 9.3. Yeah, that's right. That's right. But that's pKb for the conjugate base. This is pKa for the acetic acid. That's my abbreviation for acetic acid. And this is the pKb for the conjugate base. Okay. All right. So in case you need those values, you know how to find them. All right. All right, let's digress for a moment. And let's say you have we want to form a compound with these ratios. Right? And you're given, oh, I don't know, these two pairs. Right, there's one pair. And let's say another pair. And let's say another pair. And another pair. Which one of these two would combine to give you these molar ratios? If this is X and this is Y. This goes way back. And just to check on whether you remember these things, what are the accepted charges on these elements if they're in, and that has to be an ionic compound because these are all metals and these are all non-metals, right? So this is 2 minus, 2 minus, 2 minus, 1 minus. This is 3 plus, 3 plus, 2 plus, and 1 plus. Okay. So what you need is something that will give, that requires 3 of these to every 2 of those. Right? This one would give you that. This one would give you, what do we do when we have odd even on the other side? Cross multiply. So this would be 2 and that would be 3. Oh, you got your answer right there. That's it. This would be that, and this would be that. Okay? Just a refresher course. All right, let's say we have this reaction. Now we're gonna kind of slide over into kinetics a little bit. Let's say we have this one. That's a gas. And it produces this one. They look the same, don't they? But actually they're not. Right? This one would be like that. And this one would be like that. So the hydrogen is bound to the carbon, and this one is bound to the nitrogen in that one. So it's a valid reaction, in case you're wondering. All right. So how would we express kinetics for this reaction? Right? The rate, right, if we had this one, initial rate reaction, and it would disappear, right? Because there'd be none of that to start with. So the rate would be some constant times H. Yeah. To some order, right? And the order is not derived from the overall reaction. Okay, so what's possibilities? Well, if it were zero order, what would we see? So zero order, and let's see, we could have zero order, first order, or second order. Those are the only ones we've studied. Zero order would look like what? Well, this is going to be disappearing. So if we plot against time, then the absolute concentration of that would disappear over time, right? It would be a straight line if it were zero order. And if it were zero order, then the rate would only depend upon K. If it was first order, then the plot of the natural log of H in C over time would be, I don't know, something like that. That looks like the same slope, but it's not supposed to be. If it were second order, what would it look like? Well, it would have to be the inverse. With time, and that would go the other direction, right? Because when we invert the term, then as it disappears, the inverse gets bigger because this gets smaller and smaller and smaller and smaller. So that gets bigger and bigger and bigger. Okay. So if the question is, say, this reaction is second order, then if you were given these choices, you would pick that one. Okay, let's just overview. Let's see. What else can we say about this? One second. Okay. We can also say that the well, we can derive let's see, well, I erased it. The equation that I put up there before was the differential equation. We can also use an integrated equation, which incorporates time. And for this one, the concentration of at any one time is the negative K value times time plus whatever it was at the beginning. Okay? So the slope on this line is going to be a negative K. So if you're given actual values and you're told that it's either zero, if you're told it's zero order, then all you have to do is calculate the slope of the line and you have K. Or we could say that the half-life is equal to, let's see. Yeah. Over 2K. And all this stuff is in useful information. When you take the exam, in that folder, there are going to be several documents in there that you can access. If it was first order, then of course it would be in terms of the natural log. All right. And the half-life then for that one is 0.693. Okay. And then for second order, this would be inverse. Would be a positive K. And then the half-life would be there. I know it's kind of jumbled. But in order to find the K for each one, you just need the slope of the line. In this case, it's negative K, negative K. In this case, it's positive K. Also, you can see that from the half-lives are all dependent upon the inverse of K. They're proportional to the inverse of K. Now, there are other factors involved, like this one doesn't even, the half-life here doesn't care. If it's first order, it doesn't care about the initial concentration. Half-life's going to be the same no matter where you start. But for these, depends on where you start as to what the half-life will be. They're still dependent upon the inverse of K in each case. Let's see. Do I need to leave any of that stuff up there for discussion purposes? No, okay. Now we actually backed up. We were on acids and bases, which is beyond equilibrium. And then we moved back into kinetics. Now we're going back in further to the very beginning and propose a question. Let's just suppose we have nitrogen gas. And we're going to cool it down and compress until it forms nitrogen liquid. Okay. Why does it form a nitrogen liquid? Right. We know about intermolecular forces, right? So we could have, we can choose from intermolecular forces that are either ionic, right? Polar, or what's the last one? Or London dispersion. Okay. You could have two ions attracting, positive and a negative, or you could have two polar compounds. Well, if we're talking about a pure compound, of course, it's polar-polar or ionic. If we're talking about mixtures, you can have ionic attracting polars and so forth. But let's stick to pure situations. In London dispersion, oh, by the way, what are the strongest forces? Strength increases this way. Right, so these are the strongest, next strongest, London dispersion. And of course, polars, and they're really on a continuum. When do London dispersion forces occur? Always. London dispersion forces are always there. It's just, in relative terms, how significant are they? Right? If you have polar or even ionic, London dispersions are virtually non-existent. I mean, we know they're there. They just don't contribute to the attractive forces very much. Only when these are non-existent, the London dispersion forces account for any intermolecular attraction. And that would be the case here, because what do you have? Nitrogen, like that. It's not ionic, definitely. There's no ions there. It's not polar. Why? Because the bond's not polar and the molecule is symmetrical. Okay. Example of water's a good choice, right? The bonds are polar here, and the molecule is asymmetrical. So you get an overall dipole like that. That's why water is polar. But nitrogen's not polar. Which means that as it cools down, the only forces it has to work with are London dispersion forces. Now, what if London dispersion forces weren't there? Right? You could cool and compress nitrogen all the way down to nothing, and it would still be a gas. And you can, depending on the strength of those London dispersion forces, you can form a series of compounds based upon their melting point or boiling point, whichever the case may be. Let's see. Okay, that's the only point I wanted to make there. Oh, well, one more point. When I drew water, that's a special case. It is polar, yes, but it's on the strong end of polar. because it has available to it hydrogen bonding. Hydrogen bonding is a special case where you have some electronegative element bound to hydrogen over here. And that could be, in water's case, it's oxygen. Other cases, I think fluorine would work. And sulfur would probably work also. So what that does is it forms a dipole that direction. And it's a particularly strong dipole. So that when they line up, if these are the only bonds available, then you have slightly positive and a slightly negative and slightly positive. And then the other molecules, if it's a pure substance, the other molecules line up this way, so that you have that, at least this, and sometimes even that. All right. So how are we doing on time? Okay, we're good. We'll probably finish up on Tuesday. Oh, here's a good one. Suppose we have, well, let me see. Hold on a second. Before we leave that one, it's going to take us back into acids and bases. I want to see if I've got any to work with for gases, liquids, and solids. Oh, this is a good one. Yeah, let's stay on the let's stay in chapter 10, 11 for now. Let's say we have 3 vessels. Okay. And we put a liquid in them. Okay, hold on a second. Let's start over again. Let's use flasks. Okay. Here. And there we go. 3 different size flasks. We got the same liquid in each one. Let's just say there's enough liquid in there so that after we cap it, each one, and of course they're volatile liquids, and they're all the same liquid. All right. Let's just pick something like I don't know, ether. Is that a good one? Now let's use methanol. Right. Methanol in each one of them. And we've got enough in there, so when they reach equilibrium, there's still some liquid left. Okay? Question is, what's the vapor pressure in each one? Are they different? Say the temperature is constant. Now, what can you say about the vapor pressure? The vapor pressure in each one is exactly the same at equilibrium. Right? Equal. Vapor pressure is the same, depending on temperature. What about the mass of the gas. So we have a mass of the gas, and a mass of the gas here, and a mass of the gas there. How are they related? Are they equal? Correct answer is no, right? Because they've got more space over here. You need enough mass up here to produce the pressure that's required for the return, dissolution, to balance the vaporization. And in order to do that, you need more mass up here because the equilibrium is dependent upon surface impacts. You need enough molecules up here to impact the surface to return to the liquid phase as are leaving the liquid phase. So that means you need more mass over here. So this one will be bigger than that one. Okay? All right, let's see if I've got any others. Okay, let's say we have some compound, just call it A, and it's in the solid phase. And it's going to transition into the liquid phase, and some of it may go into the gaseous phase. Okay, so each one of these steps has associated with it an enthalpy. How much energy per mole does it take to go from here to here? So this would be the enthalpy of fusion. Why do we say fusion? Well, because it can go backwards also. And this one would be the enthalpy of vaporization. So that one is going that way. This one says it's going that way, but the numbers are the same, they're just opposite signs. Okay, so if we're going from solid to liquid to gas, we're going to have to put energy into it, right? So the value going from that way to that way is positive and positive. But that's not the question. The question is magnitude. How much energy does it take to go from here to here, and why? Or from here to here, and why? To go from solid to liquid, what's happening? All you're doing going from here to here is you're disrupting the order of the solid so that those molecules can slide past one another. That doesn't take much energy. Well, I should say it depends on the molecule. It takes a pretty good amount for water to go from ice to water, liquid water. But in most cases, and we're going to talk in relative terms between this one and that one. So you're going from here to here. There's no regular order. It takes a little bit of energy. Now, how about going from here to here? What do we have here? Those molecules are way far apart. How did they get there? They got there by breaking the remaining bonds between the liquid molecules. And they're virtually independent actors, separate molecules. That takes a lot of energy to go from here to here. So the intermolecular forces involved here are such and such. What do we have to do to go from here to here? You just have to weaken the forces. To go from here to here, you have to completely break them. There are virtually no intermolecular forces. And in fact, the kinetic molecular theory of gases says, one of the premises of that theory says that there's no interaction among the molecules. They just act like billiard balls that bounce off one another. Okay. That's all I wanted to say about that one. Let's see. All right, let's do this one. This is a dimensional analysis problem, but it's good practice to work these problems every now and then. Say we have 5.2%. No, that's not right. It could be. Actually, it could be higher. Let's say we have 6.5% sodium chloride in the Dead Sea. Right. It's normally you'd have about 3.2% salt in the oceans, but in the Dead Sea, it's going to be a lot higher. I think it's about twice as high. We want to know, what is that in terms of molar concentration? Right. So what does this mean? Well, percent, remember, percent is for compounds is mass. Right, so this is going to be 6.5 grams sodium chloride per 100 grams of Dead Sea water. So what else do we need to know? Well, if the denominator is mass, you're never going to get to molarity, because molarity is in terms of mass, is moles volume. So we need a density. So what's the density of the Dead Sea water? Well, I don't know. So I'll just have to make something up. I know it's pretty dense. They say if you go swimming in the Dead Sea, you float a lot higher because the water's denser. So let's just, let's make something up. Let's say it's 1.1 grams per mil. That might be a little high, but all we need is a number. So this gram, and that's grams of seawater per milliliter of seawater. Right? So grams have to be canceled and leave us with milliliters. Okay, so now we got that done. Now let's continue with this and just make it liters, right? Because we're going to need liters on the bottom. There we go. Now we got, and this just illustrates when you have a multi-dimensional conversion that's taking place, you do one at a time. So we're going to do the denominator first. It's done. Now we want to change grams of sodium chloride into moles. And that should always trigger molar mass. Grams and moles together, molar mass. It should be instantaneous. So I'm going to have to come down here. Well, what's the molar mass of sodium chloride? Well, let's see. Let's look it up. 23, 2 decimal places. And chlorine is 3545. I know that one. So this is 45, 8, 5845. Okay, so there you go. Grams. Now we have moles per liter. And all we have to do is crunch numbers, right? That times that, 1, divided by that, divided by that. And you got it. So I'm not going to work that out. The hard part's already done. The thinking part, I should say, not the hard part. Part where you actually have to think. Okay. Pull that down. All right. Let's see if there are any others before we move on. Okay, now I'm going to go back. Yeah, we've got time. Lots of time. In fact, you may be getting bored stiff by now. Let's see, where am I? Losing track of myself. Okay. Let's go back to buffers. Why? Because buffers are extremely important, particularly for life sciences. Okay. Suppose we're given this set of data. For these weak acids, right? Dihydrogen phosphate, which would be a -1 charge, right? Because 3 of those would balance it. Take 1 away, that leaves you a minus. So the pKa for this one is 6.2 times 10 to the -8. Bicarbonate. Right? pKa for this one is 5.6 times 10 to the -11. Boric acid. Let's see. Hydrogen borate. I think that's boric acid. pKa equals 5.4 times 10 to the -10. And one more. Acetic acid. You can't leave acetic acid out. Do you want to go out? I'm going to let my cat out. He's stuck in here. Wait a minute. Let me see. Okay. Come on. You can go out. Here. Have that out. Have that out. There you go. That was 3 of them. I got 2 left. But they're being quiet, so they get to stay. Okay, pKa for this one. Oh, no, that. Nobody said anything. The Ka for this one is.
I honestly just noticed
that. I was thinking ahead of myself.
It happens.
Okay, so let's say we wanted to get it as close to neutral pH, buffered pH, not combination of strong acid, strong base, but actual buffered pH near neutrality. Which one of these would be the best choice as the acid, right? Because this means that the conjugate base is going to be HPO4 2-, right? Bicarbonate, excuse me. That's better. I say there can't be a Ka for that because it don't have any proton. There we go. That's better. Okay, so which one would be best for near neutral pH? It may not be exactly neutral, right? But if you're going to get close, which one would be your choice? Well, the best place to look is the powers of 10, because the pKa is going to dictate the best buffer pH. So if you take the pKa of this one, and we're just eyeballing it, we're getting close, ballparking. If you take the negative log of this one, you're going to get something close to 8 or even 7. Right? This one, you're going to get close to 11, close to 10, close to 5. So that would get you the closest to neutral pH. If you were looking for something in the neighborhood of 5, you would use this one. Or in the neighborhood of 10, you use that one, so forth. All right. Let's see. Before I leave this topic, do I need to okay. Now we're gonna actually do some calculations with equilibrium. So we have a weak acid, right? And it's initially we say it's 0.1. No, wait a minute. 0.01. 0.1 molar, and it's going to undergo some dissociation. Might be a weak acid, but it's still going to dissociate some. And we determine that the pH of this solution is equal to 3.76. Okay. The question is, what's the percent ionization? Thought it was going to be a hard equilibrium problem, right? No, it's easier than that. Percent ionization, we just need to say, what's our definition? Percent ionization is equal to the, well, in this case, it's 1-to-1, right? So we could use this one or that one, but we have data for that one. So this says that much, it ionizes to produce that much hydrogen ions in solution, which means we've lost this much. So how much of it did we lose? Well, we lost enough to make that, right? So it's amount of HA loss divided by total HA times 100. Okay, so we can say that we lost enough to make that many hydrogen ions. So all we need to do is say, what does that represent in terms of molarity? Well, if the pH is 3.76, that's equal to the negative log of hydrogen ion concentration. And that's what we're looking for. So we just take the anti-log of the negative. So 10 to the minus 3.76 equals, I'm going to calculate this one because I want to know what the answer is. So this is 3.76, change the sign and do the, there we go. 1.73 times 10 to the minus 4th molar. So we just plug the numbers in here, right? So the amount of loss here, let's erase both of them, is 1.73 times 10 to the minus fourth molar divided by 1.00 times 10 to the minus 2 molar. Okay, so we take 1.73 and divide by 1 times 100. So I get 1.73%. Gosh, I should have been able to do that one in my head. So that's the percentage dissociation. Okay, you've seen this one before, I'm pretty sure, on a previous exam, but we'll review it. Yeah, we're still good. What does a titration curve for a diprotic acid look like? So if we have a diprotic acid, let's use a real one. Let's use sulfuric acid. Okay. And we're going to use a shortcut. And what that's going to give us is what looks like free protons, but of course we know that these protons are attached to a water molecule. And then that gives us another proton plus our sulfate. Okay. So if we titrate sulfuric acid with a strong base, what are we going to get? What is it going to look like? So we're going to add base, and we're going to get a pH. Well, sulfuric acid is going to be a very, very low pH, way down here. And I'm not going to put values there because I'll get them wrong anyway. But I know it's going to be low. It'll be way down here. And we're going to titrate with base, and it's going to increase a little bit. You know, that's a bad choice. It just occurred to me. All right, let's do this. Doesn't have to be diprotic. Let's make it, well, yeah, okay, it could be. Boric acid. Boric acid's a weak acid. Okay, so what do we get over here? We get this one. And then we get this one. And then we get this one. There we go. Now that fits my scenario better. Okay, so boric acid is going to start off acidic, of course, but it's not going to be as extreme acid as the sulfuric. I could have used sulfuric if I were only interested in the second dissociation, but the first dissociation is complete, so it's not a good candidate for a buffer. But boric acid, yeah, that's a good one. So we're going to start off, and it's going to level off. That's this one. Then we're going to neutralize all of that one. We're going to take away all those protons. And then it's going to go into the second reaction. Produce another buffer zone. And let me shorten this a little bit. So I'll have enough room. All right? And then once all of those protons are used up, I'm going to go into a third one. Okay. So this represents the pKa1 for that reaction. This represents the pKa2 for this reaction. And this represents the pKa3 for this reaction. Okay? So whenever you have, if you see a titration curve and you see a flat and a flat, that's it. That's diprotic. If you see only one flat, that's monoprotic. If you see three flat areas, that's triprotic. Okay? Simple. And if you want to form a buffer using boric acid, but you don't want it in this acidic range, say you want it in a more basic range, then you go to this reaction, going from here to here. And when I do this, I mean, that one produces this, and then this one produces that. Okay. I don't include the proton in the next phase. Okay. Just to be clear. So you could conceivably form buffers with this triprotic acid in this region, in that region, or in that region. You just have to pick your conjugate base, right, on this side with the acid on that side. All right. Let's see what else I can find here. Standard cell potential, right? We just covered that one. So let's say we have, let's say we have two half cells, but I'm not going to tell you where they are in the diagram. Say we're going to make a battery or a galvanic cell out of these two reactions. So let's say we have aluminum okay, and the standard and say, yeah, let me pick a different. Let me pick a different. Look at my table. This will also be the reduction potential table will be there available. So let's say I want to use about let's try this one. Now, what if we have this one? Okay. And its potential is 1.36. Standard reduction potential. That would be a messy battery because this is a gas. So you would have to plumb it so you could bubble chlorine gas under 1 atmosphere into the solution. But this is all hypothetical anyway. So, which one would be the cathode and which one would be the anode? Well, we need to arrange them so that we get a positive voltage, right? we're going to make a battery. We can't flip this one because it'll make both of them negative. So it means this one has to become the oxidation. And the oxidation is, site of oxidation is the anode. So the anode would be this one yields this one. And its potential would be 1.66 volts. Right? So this would be the anode. This would be the cathode. Site of reduction, site of oxidation, add them together, and you get 3 volts under standard conditions. Okay, let's see if we got any more. If I've got any more battery questions to talk about. I thought I did back here somewhere. There will be some bonus. And of course, the bonus are going to be a little more difficult. I know I got one in here somewhere. Just have to find it. Okay. This is a good one. In this one, we're going to invoke the Nernst equation. So maybe I should write it up here. So under non-standard conditions, the Nernst equation will tell you what the potential is. If you know the standard potential, and then you introduce the non-equilibrium conditions. 0, 5, 9, 6, 10, Q. So just to make a point, if that were K, what would this be? Be 0. If that's K, that means your cell is at equilibrium and it's, for all intents and purposes, dead. Okay, so let's say we have this reaction. I'm going to give it to you balanced. I can squeeze it in here. Let's say 2. And everything's aqueous, so I'm going to leave those out, those terms out, because I really don't have enough room. There we go. And we can check to see if it's balanced, right? There are 3 hydrogens, 3 hydrogens, 3 nitrogens, 3 nitrogens. 6 plus 3 is 9 oxygens. 3 times 3 is 9 oxygens. Okay. All right, so there's our balanced equation. What we want to do is investigate under what conditions could we let's say decrease the voltage. The standard voltage we could calculate. We just need to know what our 2 half cells are like. So we have to identify the half cells before we can answer any questions. So how do we do that? Well, the equation's balanced. So We just need to know which one's being reduced and which one's being oxidized. So we need oxidation states. Oxidation state on this one is -1, right there. Oxidation state on that one is 0, but it's a +1, but this one's also +1. So hydrogen is not oxidized. It's not reduced. How about bromine? Well, oxygen in this case is a 2-, so that's 6- total. We have to save 1- for the charge. That means that this one is 5+. Okay. Oxygens are going to be constant, so we just need to decide nitrogen. So this is 2 times 2- is 4-. One of those minuses is balanced by a plus, so we only have 3 minuses. So this nitrogen is 3+. How about this nitrogen? So there's a 3 times 2- is 6-, hold 1 out. So this is 5+. Okay? So now we can tell which one does what. If we go from this nitrogen to that nitrogen, what's happened? 3+ to 5+ means it's oxidized. It lost 2 electrons per nitrogen. All right, I'm going to have to put that someplace else. Two electrons per nitrogen, and how many nitrogens we have? 3. So that's 6 electrons lost. So that means we have to go from here to here, and it should be, since it's balanced, 6 electrons gained. Let's see if that's true. 1 bromine goes from 5+ to 1-. So from 5+ to 0 is add 5 electrons, and then 1 more to minus means 6 electrons. So 6 electron gain per bromine times 1 equals 6 electron gain. Okay, so if we were going to use the Nernst equation, we would insert 6 into the N term. Minus 0.05 over N times log Q. So 6 would go in here. Let's say it doesn't matter what this is. We just want to know what effect on the true concentration would any changes in these make. You know, if we set the experiment up with different values for these, how would it affect the E? Would it go up? Would it go down? Regardless of what E0 is. So we need to know what Q is, don't we? So Q is going to be this one. Well, I put square brackets. Let's be consistent. If it's going to be Q, they need to be parentheses to the 3rd power. Nitrate to the 3rd power, and bromide to the 1st power. Then in the denominator, we would have HNO2 and BrO3. Okay? So, under what conditions, let's say we want to increase the voltage. Under what conditions? Okay. hold on a second. I'm going to pause this, and I'll be right back. I'm back. Okay. So under what conditions would say we could increase the actual voltage? What would we have to do over here? Well, we look at the term. Anytime this term increases, the log increases. That's just the nature of logs. It increases at a different rate, of course, because of the nature of the log. But if you increase this term, then the log increases. But that would have it, the impact of that change would make this negative, more negative, which would decrease the E. So what we have to do is make this one smaller. So anything that will increase these terms here and here and decrease these terms should increase the voltage. Right? So we would want to decrease the pH of our solution. We would want to have the nitrate at a lower concentration to make that smaller. Or we would have, or we would decrease the bromide concentration in whatever cell, right? If this is gaining electrons, this is the cathode. And this is losing electrons, this is the anode. So in this bucket, we would decrease that value and increase this value, for instance. In this bucket, we would decrease that value, decrease that value and increase this value to increase the voltage. And of course, if we want to decrease the voltage, just flip it. Do it the other way around. Increase those, decrease these, you get a more negative number, and your overall is a lower value for your voltage. Okay? One characteristic of these standardized tests, you may have noticed if you've taken the ACT or the SAT, the types of calculations that are required are very simple. They're really testing for concept knowledge. And with the calculations, if you can use the concept, they don't want to make the calculations too cumbersome because they've got a lot of questions to ask. So that's characteristic of ACS tests also. Just keep that in mind. It shouldn't take a lot of work to do any calculations that are required in this test. Let's see. Let's go back to kinetics. I should be marking these things off because we're going to be on 2 different days. I don't want to have to repeat myself. That one. That one. That one. Okay. All right, did that one. That one. Okay. This might be a good place to stop anyway. We're almost at 1/4 after. And we'll pick it up on Tuesday. And if you have any questions, be sure and write them down. And we'll hammer out any things that are really bothering you. If you're nervous about something you may expect on the test, and we'll work on it and hopefully put your mind at ease. But that being the case, Unless you have something else, we're done for today.
Alrighty, thank you.
Well, have a good weekend.
You too. Bye.
Bye.